Welcome, ladies and gentlemen. Let's continue with our optimization strategy. So here we're going to use calculus and derivatives, right, in order to determine the optimal solution to a problem. What's the problem here? Well, pick one, right? All kinds of problems wrapped up into this description. We're trying to figure out the maximum area rectangle that can be inscribed in a semicircle of radius 4, right? And so we can use our optimization strategy to kind of provide a focus, right? Focus for the direction of this problem as we try to use calculus to find this maximum area. All right, so what's our first step in our strategy? Sydney?
Read the problem carefully. Write down the quantity you are trying to optimize.
Why, thank you. What are we trying to do? What quantity are we trying to optimize here? Riley?
The area.
Yeah, we're trying to maximize areas. We're trying to maximize areas. So sometimes it might be minimum. Minimize the cost, maybe, of having to construct your shipping route. Minimize the weight of packaging here. We're trying to maximize area. And I like to write that down so that we provide focus for the rest of our problem. That area quantity is the quantity we're going to end up writing a formula for. It's the quantity we're going to end up rewriting a function of. It's the quantity we're going to end up differentiating and get our derivative and then analyze using a sign test. And so that first step is important to get out on the right foot. Okay, what's our second step then? All right, you guys have it out? I know Sydney does. Marissa?
Draw a picture and label relevant quantities with variables.
Bam! I've got my picture that I had fun doing with the smartboard objects, but I need to label with relevant quantities. And so I think a good way to attack this is if we center our semicircle at the origin, right, 0, 0 on the xy coordinate plane. Now it allows us to get variables involved pretty easily. So I'll go ahead and let this point where the inscribed rectangle touches the edge of the semicircle, this boundary point, I'll let that be a sample point, x comma y. Just kind of like we did with the maximal cylinder problem. So if I let that vertex point of my rectangle that lies along the semicircle be a sample point, x comma y, it'll take care of a lot of my variables for me. So once again, I'm going to copy this, maximize area as my goal. If I'm trying to maximize area, then in step 3, when I write a formula for the quantity to be optimized, right? When I write a formula for the quantity to maximize, I'm going to write a formula for A area. All right, so let's go ahead and look at our picture. If this semicircle center at the origin and the sample point on the boundary is x comma y, what then would be a formula in terms of x and y for the area of this rectangle? Right? What would give the area of that? Kobe? Yeah, if this is an x horizontal distance from the origin, then the base of this rectangle would be given by 2x. Thank you. Times the height, right? Base times height. And this sample point shows me that I'm a vertical distance of y units above the origin. And so my area formula would be 2x times y. Just really quickly, I'm going to start with my generic base times height. And then rewrite it as 2x times y just so you can see where that comes from. Everybody see that? Base times height. Awesome. But that's not enough. We need more than a formula. We need a function of one variable so that I can differentiate, use A prime, and then open up my calculus tool bag now. So I've got first derivative test, I've got second derivative test, I got closed interval method, right, depending upon what we're dealing with. So how am I going to rewrite that area formula, which currently depends on x and y, as a function of one variable, just x's or just y's? Well, what haven't we used yet? Grace?
The equation for the circle.
Absolutely. The sample point, x comma y, since it lies on the boundary of my semicircle, must obey the equation that relates x and y in the generic form of a semicircle. This is the top half of a circle, right, which obeys the equation x squared plus y squared equals r squared, where r is my radius. So if I start with my x squared plus y squared equals r squared, in this case my radius is 4, is that right? So x squared plus y squared equals 16. Is that right? Then this sample point y in terms of x would simply be given by the positive and negative square root, because I'm on the top half. I'll only consider the positive arc of that semicircle, of that circle. So I'm going to have 16 minus x squared inside of my radical. Raise your hand if you got all the way to y equals. Did you solve for y in terms of x? That's important because now we'll be able to rewrite my formula, A, which depends on x and y currently, as a function of one variable. Call it A of x with just x's in it. Here we go. We're going to substitute in my expression for y. into my area formula where I see it. So I get 2x times square root of 16 minus x squared. Can I see it? Awesome. So we've used the relationships in the problem to rewrite my area formula as a function of one variable. We're up to our strategy, and now we're all the way to step 4 now, are we? Or we just did step 4 to create that? What do we need to do next, right? What do we need to do next? Grace? Absolutely. We're going to differentiate to generate a prime, so we can use everything we know about derivatives and function behavior, right, to find the maximum here of a. So here we go. A prime equals, golly gosh. I don't think I've said golly gosh in a long time. Golly gosh. I'll say it again. What rule are we going to have to use, given that my expression for a includes that 2x and the square root of 16 minus x squared? So overall, what rule will we have to use to differentiate, Sophia? The product rule. Good. I know the derivative of a product of two functions is the derivative of the first times the second as is plus the first times the derivative of the second. Moving on, plus the first times the derivative of the second. The derivative of the second is a power rule, where the current exponent on that quantity is to the 1/2. Remember, square root is a 1/2 exponent. So, exponent times the base, raised to the 1 less, times the derivative of the base. Did we differentiate the second term correctly? All right, let's go ahead and simplify and rewrite so that we can try and utilize my first derivative test or my second derivative test or my closed derivative one. So here we go. I'm going to go ahead and leave that as 2 root 16 minus x squared. But I'll go ahead and simplify a little bit here. So whichever 2 you want to cancel out. Negative 2x times x is negative 2x squared all over 16 minus x squared to the negative 1/2 is the same as the square root of 16 minus x squared to the bottom. How many mistakes did I make in that one line? Okay there? Okay, so as we continue on, I'm trying to think about how it's going to be easiest to determine my critical values. That is, when a prime equals 0 or is undefined. And because I have a sum or difference of terms here, one of which is a fraction, I'm thinking common denominator is the way to go. If I write this as a single fraction, it'll be easy to set my top equal to 0, set my bottom equal to 0, and that'll generate my critical value. So I'm going to go ahead and construct a common denominator by multiplying this first term by root 16 minus x squared over root 16 minus x squared. Agreed? That will construct a common denominator. So we'll go ahead and do a prime equals 2, and then this radical times itself is going to be just 16 minus x squared without a radical, minus 2x squared for the right hand, over my common denominator of root 16 squared plus u. I know that this will generate critical values whenever a prime equals 0 or is undefined. One more step of simplification and we're ready to go. So this becomes 32 minus 2x squared minus 2x squared is 32 minus 4x squared over square root of 16 minus x squared. Good news. Why all the simplification, Mr. Fritz? Because now it's easy to generate my critical values. I can simply set my top equal to 0, my bottom equal to 0, and generate my critical values. Those are the values of x for which a prime would equal 0 or be undefined, respectively. So are there any values of x that make a prime equal 0? Well, certainly. It looks like 4x squared equals 32. So x squared equals 8. So x equals plus and minus square root of 8. And x equals plus or minus 2 root 2. if we restrict our original function's domain to be, what's the maximum value of x that I could go before I run out of semicircle? 4. So if I restrict my domain to be from 0 to 4, then I can just take the positive 2 root 2 and do less tests. So I'm going to go ahead and restrict my domain from 0 to 2 and 2 root 2. Are there any values of x for which the denominator equals 0? Yes, if x equals plus or minus 4 with the restricted domain, we'll only take the 4, and that happens to be an endpoint of my interval. So it looks like I can get away with the number line, right, with the sole critical value, 2 root 2. You guys agree? Let's go ahead and construct a number line for a prime then. On the a prime number line, which we can cap to 0 to 4, we'll go ahead and put 2 root 2. Recall that root 2 is like 1.414, so 2 root 2 is like 2.818, so I'm going to go about here. And now I'm going to try to do this analytically, knowing that I could certainly use my home screen if we're just trying to get a decimal approximation or something to verify our findings. Again, we're trying to balance the use of non-calculator analytical methods with calculator allowed. So let's go ahead and see convenient x value between 0 and 2 root 2. How about 1? Where am I going with 1? I'm going into my a prime fully factored expression, or I'm going to my a prime fraction here. If I put in 1 for x, I get x squared is 1 times 4 is 4. 32 minus 4 is positive over positive is positive. So a prime is positive on the interval 0 to 2 root 2. Yes? I'm going to choose a convenient x value to the right of 2 root 2. So we just decided 2 root 2 is about 2.818. So I'm going to pick 3. 3 in for x. 3 squared is 9. 4 times 9 is 36, and 32 minus 36, right, is negative over, and if I put in 3 here, then this is still 9. 16 minus 9 is still positive. Square root of positive is positive. So I get negative over positive overall is negative. What, if anything, have we learned? We know a must be increasing up until critical value 2 root 2, and then decreasing, verifying that we have found the x value of my rectangle that will make a maximum area, right? A maximum area. Cool. So what are we going to do? I'm going to undo this so I can delete that. It's not finished. So we're going to go ahead and figure out what my area would be when I put in 2 root 2, and that'll be my maximum area possible. So what do I put in? 2 root 2, I can put it in right there into my area function and see what we get. Yes? So 2 times 2 root 2 equals 4 root 2 times the square root of 16 minus 2 root 2 squared is going to be 16, and 2 root 2 squared would be 4 times 2 is 8. So I'm getting 4 root 2 times root 8. And that looks like 4 times root 2 times root 8 is root 16. Root 2 times root 8 is 16. And that's nice because the square root of 16 is 4. So we get 4 times 4 is 16 square units. That's awesome. Therefore, the maximum, right, the maximum area possible of a rectangle inscribed in a semicircle of radius 4 happens to be 16, or 4 squared. Coincidence? I don't know. That'd be something that you could investigate further if you so choose. That's kind of neat. All right, so I've got some questions for you. Firstly, did we have to construct an a prime number line? Right? Did we have to construct an a prime number line? Tyler?
No, because there's only one.
Well, there was only one critical value, I agree, right? What was it about our function that made it so that we didn't have to construct an a prime number line if we didn't choose? Give me a hint. Is that too much of a hint?
closed interval.
Yeah, we've got a closed interval, and so we could, even if we had 3 critical values, we could still evaluate my area formula at the endpoints, that is 0 and 4, and any critical value in between, and then compare the resulting areas to select the largest one. That would still be a maximum, because the critical value is the only place where my area could switch from increasing to decreasing, so I would get all my candidates for a maximum min just by evaluating my original function at the critical values and endpoints. However, some would argue that an area, right, a rectangle is not possible to be inscribed if I choose x to be 0 or 4, and so technically we could exclude those values and then make it an open interval 0 to 4. If we had an open interval, that is from 0 to 4, we can't do the closed interval method anymore because 0 and 4 are no longer in our domain. Then we would have to make a number line so that we can guarantee that that's a maximum at the critical value to root 2. Or we could do the second derivative test. However, after our first derivative derivation, are you guys wanting to do the second derivative test? No, because I have to derive that, which looks a little bit more complicated than just doing a number line and doing my sign test. And so, depending upon the situation and what you're working with, it might be easier to do the second derivative test. It might be easier to do the A prime number line. It might be easier to do the closed interval method. I personally like to do the number line regardless, so I get a good indication of what's going on physically in the problem. So I almost always like to do the number line, but in a pinch, the closed interval method is all you need if you have a closed interval, right? After you generate the critical values, evaluate your original function at the critical values and at the endpoints to compare. Awesome. What questions you guys have on today's Bellwork? That's a great problem. All right, let's go ahead and pause the recording and take care of our OTL. Check. Thank you, ladies and gentlemen. So let's go ahead and remind ourselves about finding extrema. So when we're talking about optimization problems, we're typically trying to find an absolute maximum, an absolute minimum to fit within the problem situation. Alternatively, we could call absolute extrema global extrema. So we know that the maximum / minimum value of f must occur at one of 2 places, right? So where can my absolute, my global extremes occur, right? Where could they occur? Marissa?
Critical values.
Yep, they can occur at a critical value. Remember, a critical value of my original function f is where f prime equals 0 or is undefined. Or, Courtney, go team at an endpoint. Thanks, ladies. For that reason, right, the closed interval method can be useful for us by comparing the original function values at the endpoints and at the critical values. We can then select, right, the optimal solution. That could be a max or a min. So the closed interval method, we evaluate the function at the critical values and at the endpoints, and then compare to find the optimal solution. We could also use the first derivative test, which we used in today's Bellwork, where we construct a y prime number line with my critical values along it. We may or may not be able to cap that number line, right? And so it's fine if we don't know. If we don't know the endpoints of my interval, and then we perform a sign test on each subinterval to determine the behavior of y. And then lastly, the second derivative test. If f prime of c equals 0, we're talking horizontal tangent on f, and f double prime of c is positive, so we have horizontal tangent and right side up bowl shape, then f must have a local minimum, right? It must have a minimum at x equals c. Conversely, if f prime of c is 0, but f double prime is negative, now we're talking horizontal tangent, but upside down bowl shape, what feature must occur? Well, then we must have a local maximum at x equals c. This is fun. Cool. So we've got 1, 2, 3 different tools and our optimization strategy. Today we're going to look at some more complicated examples together briefly, and then you're going to have the remainder of the time to work on your OTL with the classmate. So long as you guys are quiet and on task, you get a big chunk of the assignment done. And I kind of wanted you to have some time in class so you could talk about it, because some of these problems are tricky. Let's get going. What's the minimum amount of material that can be used to construct a 1.5 liter cylindrical can? What? The minimum amount of material that can be used to construct a 1.5 liter cylindrical can. Go ahead with your partner right now. Complete step 1 in our optimization strategy. That is, write down what it is that we're trying to do. What quantity are we trying to optimize? And then share with the class what I'm calling. So what is it we're trying to do in this case? What quantity? All right, so what's our goal here? What's our goal here? Sophia and Kobe?
To minimize the surface area?
So minimize surface area, right? If we can minimize the surface area of this can, then we will have found the least amount of material that is used to construct it. Good, thank you. So we'll go ahead and minimize surface area as our goal. So we want to go ahead and draw a picture and label with relevant variables, and then write a formula for the surface area. So everybody, we're picturing our right circular cylinder can. All right. So there's our can, and we know our can is going to have maybe a radius R and height H. That's supposed to be a cursive H. Sorry, A, sorry, A. It's the handwriting thing catching up with me. And you guys probably want some dots there, so it's really comes to life, huh? Bam, 3D. All right, guys, based on our picture then, can we write a formula that gives us the quantity to be optimized, that is surface area? Go ahead and decide with your partner what that formula would be. Blast from the past, you might have to put your heads together to come up with this.
Use the circumference.
Sorry.
No.
Yes.
Oh, yeah, that's for one.
Okay, so we do, so first define the area of this, we do 2 pi r, so yeah, the circumference times height, range.
No,
You need
that's
to
not
find
it.
the area.
Do you guys have it?
And you do.
Yeah, you got it? I think. Okay, guys, what formula then? What formula are we going to use for the surface area? What formula are we going to use for surface area? Danny and Emily?
2 pi r times height plus 2 pi r squared.
Could you briefly explain where you got each term in your formula for A, the surface area of my can?
The first part is the area of like the side.
So the sidewall then would be given by 2 pi r. I'm seeing that's familiar from a circle, right? That's the circumference times h is height, right? So that's like one big rectangle. If I were to cut along the sidewall and fold it out, I'd have 2 pi r wide times h high. Good. Keep going, Danny.
And the second part is the area of the top and bottom.
Thank you. So there's 1 pi r squared on the top of the can and 1 pi r squared on the bottom, so it's 2 pi r squared total. Raise your hand if you have the same formula. Same formula? Yes, okay, good news. Now we need to use other relationships in order to rewrite that formula as a function of one variable. Right now my surface area A depends on r's and h's, right? Pi is a constant, 2 is a constant, so we just need to figure out how to rewrite this in terms of just r or just h, right? And it's our choice. What do we know about the can? What other relationships do we know about the can? Courtney?
The volume has to be 1.5 liters.
The volume has to be 1.5 liters. And so regardless of my dimensions r and h, they must adhere to the volume equation that produces 1.5 liters. Recall the connection with SI units, right? And why we work with SI so much in the physical sciences is that a liter, right, is 1,000 milliliters, and a milliliter, right, is a volume unit, but that's equivalent to what? A cubic centimeter. So that's going to allow us to get our dimensions here back towards the centimeter, right, aspect, and so that's useful. We could go ahead and say that our 1.5 liters is equivalent to 1,500 cubic centimeters, yes? So my volume V of a right circular cylinder is given by base area times height, so pi r squared h is my volume, right? Is my volume. That's not to be confused with my surface area, right? This is different. This is my volume. And I know that 1,500 must equal pi r squared h. All right. So is it going to be easier to solve for r? Is it going to be easier to solve for h in this volume formula? What do you guys think?
H.
H I'm down. We can do that one step by dividing both sides by pi r squared in one step. And so h is given by 1,500 over pi r squared. We can now substitute this expression for h into my surface area formula everywhere I see an h, which is only one place, so that I have a as a function of one variable, a as a function of r. Then for ease of writing, I can replace that r with x and call it a formula a of x and be working with my a prime of x just like we did in Bellwork, if we so choose. So I'll rewrite this now as a of r equals 2 pi r plus 2 pi r squared, and my big parentheses h is 4 1500 over pi r squared, yes? That's what we're putting in for h. Again, I think it's useful to go ahead and do some rewrites to make a simple expression before we do our differentiation. I'm going to, at the same time, make it a of x. We don't have to, but I'm going to. We can do some cancellation. We can do some cancellation here, too. So 2 and, nope, 3,000, pi, and one of the r's, so we can at least make it a little simpler. I'm getting 3,000 over x. Is that what you guys are getting if we change our r's to x? Is that good? Plus 2 pi x squared. Yes? She? Okay. So we've generated a formula. Now we can consider our domain of this. Oh, we've replaced one of the variable quantities in my formula now, so that I have a function of a single variable. Now I'm ready to consider the domain of this. Do I have a closed interval in this particular problem? No, right? Technically, we let this can be as tall and skinny as we want, or as short and squat as we want, right? But yes, Sydney, squat is a funny word. Squat is a funny word. But the end result is we don't have, right, a closed interval. So 0 to infinity, we really don't have a closed interval, so we're not going to be able to utilize the closed interval method. No problem. We've got 2 other bags in our calculus. I'm sorry, 2 other tools in our calculus tool bag. All right, so what are we going to do? A prime. Let's do it. So a prime of x equals the derivative of 3,000 over x is the power rule, negative 3,000 over x squared. Plus the derivative of 2 pi x squared is 4 pi x. Is that right? That's pretty easy. Did I get more space? I'm going to copy again. This time I get the whole thing though. And now we want to see when this a prime expression equals 0 or is undefined. So what do? Well, I'm going to rewrite it as a single fraction. So I'm going to make this multiply top and bottom by x squared. Yes, to create a common denominator. Are you down? And I'll get 4 pi x cubed minus 3,000 all over x squared. How do we do? How you feeling today? Is that okay? Where does a have critical values? When a prime is equal to 0 or undefined. So I'll consider, does the top ever equal question mark 0? Does the bottom ever equal question mark 0? Well, yes. When x equals 0, a prime is undefined, but that doesn't really help me because 0 is not in the domain of my expression I'm dealing with. 0 to infinity, don't really have a closed interval, or we couldn't construct a can, right? That would hold any volume, right? Let alone 1.5 liters if I had 0. And so this result, x equals 0, is trivial and doesn't help us. What about the top? So let's see. Does 4 pi x cubed ever equal 3,000? Probably. If x cubed equals 3,000 4 750, 100, 750, 750 over pi. Yes? Is that right? Happens when x equals the cube root of 750 over pi. Well, the good news is there good news? The good news is that there's just a single critical value, right? Cube root, I don't have to take the positive and negative square root, it's just the cube root. of 750 over pi. So we don't have a closed interval. We can't utilize the closed interval method. What else can we do to analyze this? Well, what's another one of our tools? What's another one of our tools? Sydney?
The first derivative test.
We can do first derivative test. What's another one of our tools? Riley?
Second derivative test.
Second derivative test. Which one's going to be easier in this case? Well, I don't know. I could do both and then see after the fact which would have been the better case to go. We haven't used the second derivative test really, right? But we do know when a prime equals 0, and so maybe this is an opportunity to utilize the second derivative and see how that works. What does the second derivative test say? Well, if I go back to that a prime expression in red before I rewrote as a single fraction, I think differentiating this red a prime might be easier in this case than trying to do a sign test on either side of this critical value without a calculator, because I don't know what that is. You know what I'm saying? And so if I'm working non-calculator, this might be a situation where the second derivative test is actually useful. Let's go ahead and generate a double prime rather, by differentiating a prime. So I'm going to differentiate the a prime that's in red before I made a common denominator. Let's see how that works for us. Ready? A double prime of x equals. What rule will I use to find a double prime? Well, I'm going to use power rule, and I'm going to use the derivative constant function, right? So this current power for a prime, I'm just going to rewrite this to make it easy. It was 4 pi x minus 3,000 x to the negative 2. Yes? Is that my current a prime? I can use the power rule to differentiate each of these, and it's pretty simple. What's the derivative of 4 pi x with respect to x? 4 pi. What's the derivative of negative 3,000 x to the negative 2? Well, exponent times the base raised to 1 less. This gives me negative times negative is positive 6,000 x to the negative 3, which means that a double prime of x is just 4 pi plus 6,000 over x cubed. You guys see it? Why is this helpful? Well, because now, if we can evaluate this expression at the cube root of 750 over pi and determine the sign, whether it's positive or negative, that will tell me if we're doing a max and min without having to do an a prime number line and work on either side of that critical value, which I don't know what it is. You see what I'm saying? All right, let's do it. A double prime evaluated at cube root of 750 over pi equals 4 pi plus 6,000 over, what is the cube root of 750 over pi cubed? 750 over pi. Do I need to go any further? Well, do I need to know exactly what a double prime of cube root of 750 over pi is? No, I just need to know what about it. If it's positive or negative, and I see clearly that this must be a positive result. Therefore, a double prime of cube root of 750 over pi is positive. And that's all I care about. So since a prime of critical value equals 0, I've got a horizontal tangent, and a double prime of critical value is positive, I'm dealing with what feature? Concave up shape would be what feature at x equals critical value? A minimum. So A has a minimum at radius r equals centimeters. All right, now I still don't know what that is, but we have to go back to the question. What is the minimum amount of material? So it looks like we do have to evaluate one more thing. We need to evaluate what? A. We need our original area. surface area, bless you. And so I am gonna have to evaluate A to finish out the problem. And for that, I will use the calculator. Come on, I made this up yesterday. It can't be that far. I wanted to see when the heck to use the second derivative test, right? So I wanted to do one where it made sense to do the second derivative test because we never used that one. But I think it makes sense in this one. Yeah. All right. So I'm just curious what that is about. And so if I were to go ahead and enter my critical value. Nope. Cube root of, and I want 750 over pi. Now I can evaluate my function. So that's about 6.204 centimeters. So my area then would be given by 3,000 over critical value plus 2 pi critical value squared. Is that right? So it looks like the least amount of material that can be used is about 725.396. What would the label on that be? Square centimeters. Awesome. Good job, you guys. I thought that was pretty awesome. All right. Now, certainly we could verify graphically using the built-in capabilities of a grapher and second calculate minimum, just like you did with the maximal cylinder exploration, and balance the two non-calculator versus calculator allowed methods. But I think you guys are good with that. All right. So where does that leave us? Well, we can hold off on this. I wanted to get you some practice time, and so again, we'll hold off on this. And let's close it up for the day so that you have an opportunity then to work together. I want you to be able to verbalize some of these problem situations because that's going to help you generate your relationships. Okay, ladies and gentlemen, thank you. Let's go ahead and share a brief description for the second derivative test, right? What's the second derivative test look like? Vivian? Awesome. If y prime equals 0 and y double prime is greater than 0, then y has a minimum. Awesome. And the other one is if y prime if y prime equals 0 and y double prime is negative, that is less than 0, then y has a maximum. Thank you, Vivian. Do you prefer the closed interval method, the first derivative test, or the second derivative test? Why? Well, who wants to share something? Sydney.
I like the first derivative test.
And why?
Because you're going to construct a y prime number line. So it'll be like, oh, I like that.
I like that too. By looking at my y prime number line, I can see exactly what y is doing in terms of increasing versus decreasing, and for me, that's easier to visualize a maximum versus minimum extreme. Anybody like something else better? Kobe.
I like the closed interval method because you don't have to do this.
Because you don't have to find an x value. Sometimes it's inconvenient to find a convenient x value on each subinterval and evaluate in your a prime expression or your y prime expression, particularly if your y prime expression is difficult, right? Excellent. Anybody pick the second derivative test? Yeah, not a favorite, although it was useful in our last example. All right, you guys, we've got 1, 2, 3, a whopping 4 problems today, up from our 3 problems yesterday. How come? Because these are tricky and they take time. You may work together, but please keep the noise level down and make sure that you're on task and using AP Calculus time for AP Calculus. Okay, I'll go ahead and save the recording up here on our Moodle page. Nice work today. Thank you.